Let us now wrap up what we have learned in this unit. First, we have discussed different force types. Again, a large variety of closures exists, ranging from contact forces to non-contact forces such as cohesive forces to fluid-induced forces. Some of these closures require additional models to be solved. For example, if you're interested in fluid-induced forces, like the drag force, of course we need to have a computational fluid dynamics or CFD model at hand. Another example would be electrostatic non-contact forces. For these forces we have to know, for example, the charge of the particles and the electric field strength. If we don't have this information, the best we can do is to assume something about the fluid flow or assume something about the electrostatics and then give input to these closures. A very important aspect are normal contact force closures. Here, the coefficient of restitution is an extremely important concept that you should know. It is used to parameterize almost all contact force closures. Again, the coefficient of restitution can be measured for single particles only in rare cases. So typically this parameter is calibrated. Later, this calibration procedure will be explained. Important is that no one is perfect, as in real life. Each closure has its pros and cons. For example, for the hysteretic elastic force closure, we need more memory in the normal direction because we have to store the maximum overlap. Some closures cannot produce some limiting cases. Here we also have to take this into account if we select a normal force closure model. For example, if we apply a Hertz normal force closure, it might be the case that it's not possible to model a constant coefficient of restitution. In order to choose the correct time step, it's very important that you are able to calculate the contact time and the coefficient of restitution for your normal contact force closure. This is of extremely high practical relevance for conducting DEM-based simulations. In a supplementary material you find more details about this and how you can do these calculations. If we now switch over to tangential contact force closures, it is important to note that this is a non-trivial exercise. The simple example with the shear forces that I showed you before is a very good start to understand that these contact force closures in the tangential direction need special attention. The last model that I've shown you in the tangential contact force closures uses a spring element. And this is typically preferred because this is the only way to really model enduring stick contacts. If you use a more simplified model that only uses the tangential velocity, the delta t dot, this cannot be guaranteed. In short, if you want to have a realistic tangential force closure, you must be able to calculate the tangential overlap. This requires memory, and the tangential overlap calculation, as indicated before, needs to be integrated from the tangential relative speed that is available from the current particle velocity in the translational and in the rotational direction. The good news is now that you are now ready to start a first DEM-based simulation and make a proper selection of force closures. We don't have all the details at hand, as I mentioned already, but I highly recommend you now to start a DEM simulation if you have installed the software already. So let's do this now in the next unit.